Welcome to a lecture video, and this is brought to you strictly for Math 146. It's brought to you by Mr. Thomas, and we are live on YouTube. You should be able to access this video anywhere at any time, and we are going to jump into Chapter 5 stuff. So it's going to get really good, and I'd like to kind of really explain the inner workings of the formula so that when you use the formula, you're aware of what it's doing and you're not just punching the formula into a calculator or just applying this long complicated formula. You actually know the inner workings of the formula. So we're gonna work on that today. So that is binomial probability distribution. We are now in 5.3 and we are making good progress. 5.4 we will cover that one as well, but in this video it's strictly binomial probability distributions, and we will look at the binomial probability function as well. Okay, so really interesting stuff. So pretty excited to get into this. Double check the settings, make sure everything is up and running according to as it should be. Okay, so now what we're going to do is look at some of the key concepts that we will study in this lecture video. So it says this section presents a basic definition of a binomial distribution along with notation and methods for finding probability values. Binomial probability distributions allow us to deal with circumstances in which the outcomes belong to two relevant categories, such as acceptable, defective, or survived died. A binomial probability distribution results from a procedure that meets all of the following requirements. Okay, so it becomes pretty important to be able to know a binomial distribution when you see one, and there could be exercises to where you have to determine whether or not something is a binomial distribution. So for the first requirement, is the procedure has a fixed number of trials. The trials must be independent, and that basically means the outcome of any individual trial doesn't affect the probabilities of the other trial. Each trial must have all outcomes classified into two categories. And again, that's the pass-fail. We commonly call this or refer to this as the success and failure. So probability of success, probability of failure. So kind of like an on-off switch. And then the fourth, the probability of a success remains the same in all trials. So let's look at some notation now for this binomial probability distribution. So we refer to S and F as success and failure, and they denote the two possible categories. So for all outcomes, P and Q will denote the probabilities of S and F. So the probability of success is P, we'll call it little p, to represent the probability of success, and the complement of the probability of success is the probability of failure. So that's going to be 1 minus p, which we'll call q. So it turns out p plus q will add up to 1 whole. So let's look at some more notation. N represents the number of fixed trials. X denotes a specific number of successes in n trials. So x can be any whole number between 0 and n inclusive, and P denotes the probability of success in one of the n trials. Q denotes the probability of failure in one of the n trials. And then finally, P of x denotes the probability of getting exactly x successes among the n trials. So caution, be sure that x and p both refer to the same category being called a success. And then finally, when sampling without replacement, consider events to be independent if the sample is less than 5% of the population. So when you're sampling without replacement, consider events to be independent if, again, the value of the sample size is less than 5% of the population. We can still consider them to be independent. All right. So what we're going to do now is look at some examples of things that could be binomial distributions. Let's say, for example, we randomly select an adult. So we have some number of adults. It could be the population in America, anywhere. And we know that there is an 85% probability that this person knows what Twitter is. So we did our research, we've calculated the probabilities that Twitter is known amongst 85% of all adults. So suppose we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. And then the question is, does this procedure result in a binomial distribution? And then the question is, yes, or the answer is yes, it will, because there are 5 trials. They're all independent, so each adult is a trial. Each trial has 2 outcomes, and there is a constant probability of 0.85. So we can actually calculate this probability out. Now, the problem becomes, though, is that we're dealing with a group of people, and there's a lot of different possibilities and combinations on how we can get the correct probability. All right, so again, imagine we had 5 people and we want to calculate the probability of exactly 3 of them that know. So let's look at how we could actually break this problem down a little bit. So I'm going to write out some important information. We know that the probability of success, which we call P, that's actually 85%. And then the probability of failure is Q, and that's going to be 1 minus 85%. So we know that that's 15%. And so now the question is, well, what do we do with the 5 people? So let's say we had 5 people. We have A, B, C, D, and E. Well, it turns out there's a lot of different combinations of 3 people that may know it. I mean, for example, it could be that the first 3 may know it and the other 2 don't. So 0.85%, 0.85%, 0.85%, and then these 2 do not know it, so I do 0.15, 0.15. And I would calculate that probability by multiplying them all up. Multiply all of those. But the problem is that's not going to be the probability, because it could be that B and C may not know, but D and E does. So it really boils down to how many combinations do we have? And I'll put combos. Do we have of 3 out of 5? So I'll put out of 5 members. And so, like, if we were to, I guess, let's see if we can chart them out really fast. So this is actually a pretty important problem. If I could list out all 3 out of the 5, and they'll be considered successes. So out of a set of A, B, C, D, and E, I could have A, B, C. I could have A, B, D. I could also have A, B, E. That was a lot right there. Now, aside from that A-B combination, we could also get A-C-D, A-C-E. Now, I don't have to do ABC again or ACB because that was already covered in here. So now let's look at another case where we have A, D, E. Now, aside from that, these all have A's in there, but what if it started with B? So let's do B's now. B, C, D. I can do B, C with E. And then finally, how about I have, let's see, we did B, C, D, B, C, E, and let's try B, D, E. Now, are there any other combinations that we can have with B that haven't already been covered? Well, because these B's appeared in here, if we include A, it's already going to be covered in this set. So those are all the different combinations with just B. Let's look at some others though. What about C? I could do C, D, E. Now the question is are there any others? Are there any more combinations of threes that I can get? What about if I started with D? Well, if I started with D, it would be equivalent. I would have already covered it already somewhere along the line. So let's count up all of these. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it turns out there's 10 combinations. So if we had just did this probability, we'd actually have to do this 10 times. I'd do 0.85, 0.85, 0.85, 0.15, 0.15 for the other two. I would give all these 0.85 and the other two would be 0.15. But what we're going to do is generalize this. So what we'll have to do is take the probability of this, add it with the probability of all 10 combinations. Or the binomial probability distribution will generalize this and say, well, you know what? We know that there's going to be 10 combinations. So why don't you just take that probability, multiply it by 10, and take them all to the same power, and that will be the probability. And so how we would handle that is we'd say it'd be 10 times 0.85, and we know it's going to be to the third power, and then times 0.15 to the second power, because we knew that there would be 3 successes and 2 failures out of the 5 total, and there's 10 different combinations. And when we calculate this out, that would actually give us the correct probability. And let's work it out and see. So if I did 10 times 0.85 raised to the third power and then times 0.15 raised to the second power, simplified out that way, I can get the correct probability. So it turned out to be pretty low. The probability of this happening, according to our formula, is 0.13 or 13%. All right. That's pretty much the gist of it. We're going to get into how can we actually calculate the probabilities better and faster, but that's kind of the gist of where we're going with this. So what we'll do now is actually look at the method for finding probabilities, and there's different methods. One method is, again, the formula, and also another method is using our technology. So method one is the binomial probability formula. And this is that whole expression, n factorial over n minus x factorial times x factorial. This is the combination. So if we have 5 and we have to select 3, or 5 choose 3, this is the formula that we would use. And then the probability of success to the x power times the probability of a failure to the n minus x power. and this is for the number of trials that we may have. And here are the meanings of everything there. So make note of this formula. This is a pretty nice formula to know and to see how it works. We'll work out a few problems with this formula. And I'll go over this symbol where it says n factorial. What does that really mean? The other method is using technology. Of course, we will see this method as well. There's several different technologies that we'll use. Obviously, we'll use our Texas Instrument to actually get it. There's another way, and this is using the table. So back in the day when there was no technology that people had access to readily, they had tables, and from the table you were able to create the binomial distribution and calculate certain probabilities. I may demonstrate this use as well. I think it'd be important to see that. So now let's look at some of the strategies on how you should approach these problems. Quite frankly, you should be familiar with how to do it on your calculator, how to do it with the formula, and if nothing else, how to use the table and get the answer. So now what we'll do is actually we'll do a problem, okay? And we're going to take that same problem that we talked about. And the problem is it says, given that there is a 0.85 probability that any given adult knows what Twitter is, use the binomial probability formula to find the probability of getting exactly 3 adults who know of Twitter when 5 adults are randomly selected. Alright, so we have all the important information. There are 5 people, 5 independent values. We're choosing 3, so it's out of 3. We need to find the probability of getting exactly 3. And we know the probability of success is 85%, the probability of failure is 15%. Okay, and you can get that 15% from 1 minus 0.85 because we know these two add up to 1. And so now we're going to apply that formula, a big old formula, and this is what it means. The probability of 3, of getting exactly 3, is 5 factorial over n minus 3, 5 minus 3 factorial times 3 factorial times 0.85, 3, 0.15, 3. So it's listing all the combinations. It turns out the number of combinations is 10. The probability of 0.85 to the third power is 0.614. The probability of 15 to the second power is 0.02. And when you multiply all 3 of those together, you're going to get 0.138. And that's exactly what we got when we did it by hand. The only difference is we didn't use the formula to get the combinations. All right. So that formula is also available in our calculator, but quite frankly, we may not need to use it all the time. Now, a word about this formula and how it really works. There's really 2 pieces that you need to be aware about this formula. The 2 pieces are the first piece, and this calculates the combinations or the number of different outcomes. It's always going to be a whole number. And then this piece is you're multiplying the probabilities up. The probability of X successes among n trials for any one particular order. And that's how the formulas work. Okay? So what we'll do now is take a look at, let's take a closer look at working it out by hand again using the formula. And let me come on down a little bit further. So we were looking at that formula quite a bit. The formula was 5 out of, actually I'll say 5 choose 3. So it's a group of 5, but we're choosing 3. So 5 choose 3, there's a special formula for 5 choose 3. It's written like this. And this is the combinations. And so on our calculator, let me pull that up again. There's actually a button that will let you do 5 choose 3, which means if you have a group of 5, how many combinations can we select? And the C, basically the choose, represents the combinations. So we go into math, and we go over to num. All right, actually all the way over to PRB, because we are dealing with probability. And you can see the third choice, it says NCR. That is the one that we're going to choose. Now the problem is that when you choose this one, you actually have to put in the number that you want first. So I'm going to put in 5 first, and then go into math, go over to PRB, number 3, and then do 5, choose 3. So this is going to give me, it should give us 10 when we select this. Okay, so that's how many different combinations there is. And this formula, and let me write this down so we're all aware that this formula NCR is equal to n factorial over n minus r factorial times r factorial. And we were using it in terms of NCX, where x is the exact probability. Again, n factorial over n minus x factorial times x factorial. So those are the different cases. We got n choose r, and we also have n choose x. And so we got n factorial over n minus r factorial times r factorial, and then n factorial over n minus x factorial times x factorial. And so by definition, this is how it works. There's another terminology by shorthand. Sometimes you may see this. And this simply represents 5 choose 3. And it's equal to that. It's kind of shorthand because this is too tedious to write out. Sometimes this, again, is a faster way to write it out as well. So if you have 5 choose 3, that's the same as saying that you have 5 choose 3. And it's the combinations of selecting them. Now someone may say, hey, well, what's the difference between combinations and permutation, right? There's two. There's the combos, and then there's permutation. And again, permutation is when you're looking at every possible outcome. And there's really two times when we're talking about with replacement or without replacement. So if someone says, let's say I have a word, say ace. How many different ways can I rearrange this 3-letter word? How many different ways can I? Well, this is more of a permutation type of problem. In other words, if I list them out, how many different letters can go in here? An a C, or an E can go in here. So there's 3 different possibilities. Now, in the second spot, how many different values can go in here? 2. And then the last spot, only 1. And so if you multiply those together, it turns out to be 6. So there's actually 6 different combinations of words that I can form. This is called permutation. So the formula for permutation, actually, first of all, let's get into factorial. N factorial is equal to n times n minus 1 times n minus 2 dot 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 all the way down to times 1. So for example, if I have 4 factorial, that's 4 times 3 times 2 times 1. If I have, let's see if we can make some more space here. 5 factorial is 5 times 4 times 3 times 2 times 1. Now if we actually work that out, I'm going to get 20 times 6 times 1. 20 times 6 is 120. Now, probably you're thinking, well, wait a minute. Do I actually have to do all that now? No, you don't. There's actually a button for that. If you go into 5 and then back to math, PRB, you see number 4 represents factorial. It's an exclamation mark. That's this symbol. So 5 factorial means 5 times 4 times 3 times 2 times 1. And so the formula for 5 choose 3 is actually 5 factorial, but then we're dividing by 3 factorial and 5 minus 3 factorial, which is 2 factorial. All right. And because we need to divide out the repetitions. All right, so there's a way to derive this combination formula, but it does come from factorial. Permutation, on the other hand, I mean, Again, this would be a permutation problem if I did, let's get back on here real quick, and if I did this problem as permutation, I would do 3p3 is actually um, the formula is 3 factorial, and then 3 minus 3 factorial, which is actually 0 factorial, but I believe that's defined as 1. So 3 factorial should be 3 times 2 times 1, which is just 6. Let's work it out and see what happens. So I'm going to do 3 and then back to math, 2, and then 3 again. So 3p3 is actually nothing more than just 3 factorial. So if I did 5p5, that's the same as 5 factorial. But the problem is we can cut it off. We can make it short. Like, let's say I have 5, but I want to list only 3 of them. So let's say we have the numbers. Well, yeah, the question is let's say we have 3 different numbers, so 3, 2, 1. How many permutations of twos can we have, of two digits can we have? So the question is how many permutations of 2 digits numbers we can form. All right, now, how would we handle this problem? Well, we already know that there's only 3 possibilities. So the number, thankfully for us, the numbers are small. We're only dealing with 3, 2, and 1. And there's 2 different possibilities. So the question is how many values can go in the first spot? How many different letters can go, or different numbers can go in the first spot? 3. How many different can therefore go in this next spot? Well, one's already taken, and so there's actually 2 left. And you just multiply them up and you got 6 again. So it's actually 6 different values. And we can do that by using our formula 3p2. Turns out to be 6. All right. Now, if we listed them out, we'd get 6, but that's a lot of work. And especially, it's more valuable when the numbers are more, or if we had letters, there'd be more often. Let's look at one more application of this before we try to wrap it up. Okay, so what is going on? It turns out of the date of this recording, there is a huge Mega Millions jackpot of up to $1 billion, and the Powerball is up to nearly $500,000, and our lottery is even up to 4.5 million. And these drawings are on Saturday, but tonight the Mega Millions is being drawn, and it turns out that the cash prize is 1.8 billion. But the question is how do we actually calculate the permutations of possibilities? How do they calculate the odds? And so what we'll do is I'll go into Mega Millions, and we will look at the how do you play. So basically, it costs us $2 to play Mega Millions, and Mega Millions is in almost every state. There's a bunch of states combined together, and um, it's one drawing. So it's kind of a nationwide lottery, and it looks like they've expanded the numbers. So you have to pick 5 numbers, and the numbers can be between 1 and 70, and 1 mega ball between 1 and 25. And so if you can match the 5 numbers and the mega ball, then you're a winner. And you win the Mega Millions and you win the jackpot. There's other odds. If you can match all 5 but you don't match the mega, then your prize is $1 million, and the chances of that happening is 12.6. 1 in 12.6 million is your chance. So in other words, out of all the different combinations, they're saying what they're claiming is not necessarily combinations, but permutations. there's 12.6 million permutations. Well, let's think about this though. I mean, if we're trying to do this problem, and let's get some more paper here, a little bit more space again. And in fact, I can maybe next time I can just bring up a new sheet. We're going from 1 to 70, and the other Powerball, I'll call it plus the Powerball is 1 to 25. So if you can match those, then you're golden. And so let's see, we have 1, 2, 3, 4, 5 places, and then another place for the Powerball. Now the question is how many different numbers can go in the first spot? Well, there's 70 different numbers. The numbers 1 through 70. Now let's say 2 was chosen. How many can go in the next spot? Well, not 70 anymore because 1 has already been selected. So in the second spot, it's going to be out of 69 numbers. In the next spot, out of 68, then 67, and then finally out of 66 numbers, because the balls are drawn without replacement. Now, if it was with replacement, it would just be 70 to the 5th power. But we're pulling them out, and so this is what we're getting, the permutation. And then the question is for the Powerball, how many different possibilities could there be? Well, there's 25 different possibilities, and so there you go. You multiply this up. So this is really just a permutation problem. We're doing 70 p 5. And then times 25. Because again, 25 different possibilities can happen there. All right. Let's see if we can get the correct odds on the website by using that. So we'll come back here and let's do, first we'll do it two ways. We'll do it the quick way. We'll do 70 and then math p 5. And I'll multiply that by 25. Okay. 3.63 times 10 times 10 to the 10th power. Well, that's a lot. I mean, look at the odds there. What is that number really, right? Isn't it 363 million? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, not even. Even more than that. So we're actually going from, let me see if I can get this right. We're going from 3.63 times 10 to the, so what if I do 10 to the 10th power? 10 to the 10th power is 10 billion, I believe, yeah? 10 and then 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so that's 10 billion. And so what they're saying is it's 1 to 3 billion. Basically the way I calculated my odds. Let me write this out this way. Let's do 70 times 69 times 68 times 67 times 66. Okay, that was similar to what we had before earlier. 70 NPR5, they got 145, 145, actually 1.4 billion actually. All right. Again, 145 billion. So we have Yeah, 1.45 billion. And then if we take that last number and multiply it by 25, there it is. So we've calculated the odds tonight. Man, it is actually 1 to 3.6 billion chance. Now wait, what did it say on the website? Did it say what I think it said? The odds of winning the jackpot, the odds of winning. Okay, so these odds are not correct anymore. And it's because it's between 1 to 70. Before it used to not be that much. I think before it was years ago it was less than 70. So they may need to update their site. The chances of winning that is not 1 in 303 million anymore. No way. Now there are other prizes. I do yeah, there's definitely other prizes. Like if you get one white ball and one mega, that's $4. Two white and a mega is 10. Three, 10. Three and a mega, 4, 5. Yeah. And then again the jackpot. So it seems like the only thing to really play for is the two, getting all five or getting five with the mega. Well, this is actually pretty significant. I mean, four with the white mega, but in terms of the odds of that happening, it's so unlikely. Yeah, really interesting. Let's look at some other jackpot games. Let's say if we had Powerball. Actually, I won't go to Powerball. I'll go to Hit Five. So Hit Five is from 1 and 39, and you have to choose five numbers. They're saying that the odds of winning is 1 in 576,000. But if we pull out our calculator and do 39p 5, I get 69 million. So it's 1 in 69 million. I don't know where they're getting their odds from. Pretty interesting. I think they somehow might have changed their odds on how they're calculating their odds. All right. What I should also demonstrate really fast is how could we actually do this problem in our calculator as well? And I do have a solution for that. So here we go. Let's look at carefully if you have a Texas Instrument family calculator, and what I'll do is switch it to a newer model, clear this screen out as well. All right. And so again, our problem was there was a group of five people, and the probability of success that they know what Twitter is 85%, and we want to know what is the probability of getting exactly three people. Exactly three people. So how do we handle that? Well, you're going to go into second distribute and A. You go all the way down to A. Second distribute, and then you go all the way down to A. I actually went up to get it because I knew it was at the bottom. But you should go all the way down to A and then choose binomial PDF. Now, what does this tell you? What you have to enter in, because I have Stat Wizard on, it tells you what I should enter in. How many trials are there? 5. What is the probability of success? 0.85. What is the X value? In other words, what is the probability that I want? Like exactly out of how many? So I want to know the probability of exactly 3. So that's what I do. I put that in, and now this will paste to the home screen. Now, if you do not have on Stat Wizard, this is what you'd have to enter in. These are the parameters that you have to enter in and check, okay? It says binomial PDF. The first parameter is the trials, the second is the probability of success, and the third is your X value. If you have them in any other order, it's not going to work. It has to be this order. And you just hit enter. And again, we're getting that 13% again. All right, so I can almost create the entire binomial distribution. In other words, do every possibility. What's the probability of getting exactly 1? What's the probability that all 5 that I select is 0? What's the very slim chance? Even because the probability is so high, 85% is actually pretty high. So to get a group of 5 people and to only select one of them and that know what it is and the others do not, that is very rare. What about I could do, let me do a second entry, and then I'm going to put 4 this time. What is the probability that all 4 will know? Pretty likely. This is a 39% chance. And what is the chances that all 5 will know? %44 chance that all 5 will know. So this completes the entire binomial distribution. So if I were to create a table, I'll demonstrate this really fast, and we'll add another page. So I'm going to have x's on here, and then the probability of x is on the other side. And for 0, let me see if I can look this value up again. There's actually different outcomes. There's 0, 1, 2, 3, 4, and 5. And the probability of 0, let's see, I need to go back to my notes on that. Oh, it was extremely small. It was like 0.000076. Probability of 1, 0.002. Probability of 2, 0.02. Probability of 3, 0.13. Probability of 4, let me go back and see. What was the probability of 4? That's a good question. I think it was actually pretty high. It was 0.39 about. I'm approximating this. It goes on a little bit for more. And then the probability of exactly 5 was 0.44 approximately. So if I add up all of these, I should get 100% or 1 whole. So you just simply add them up. So already, like, this is 44 and 39 is already at 83, and then this puts me at 96, and then I'm at 96 and some change. This puts me at about 98 and change, really close to 99, and then this puts me over the top to exactly 1 whole if I were to add it up. So this is the complete binomial distribution of, so I can answer any question now. If someone says, hey, what's the probability of exactly 2 people in the group know what Twitter is? I could say, hey, it's a 2% chance. Or what if they said, what's the probability of at least 3 people knew? Well, at least 3 people, that means that's the probability of 3, 4, or 5. So I'd take the sum of these 3. I'd add them all up. Again, we already said that that's about almost 90 something percent, almost 96 something percent. I mean, if I add this up right there, that's 83 and then about 85%. So I just say about, oh, if I added that up right, I don't think I did. No, about 96%, I mean. So the probability of at least 3. Um, Sometimes they'll get tricky and say, hey, what's the probability of at most two? At most two. That would be probability of 0, 1, or 2. That's at most two, and you take the sum of them, you add them all up. That's how this section works. What we'll do now is take a quick look at a peek at some of the homework problems. So the question is given the subjects surveyed were selected without replacement, the events are not independent, can the probability be found by using the binomial probability formula? Why or why not? It says no, the selections are not independent and the 5% guideline is not met. Yes, there is a fixed number, there's so on and so forth. So this is kind of getting you an idea on, are you aware of um, the requirements? Are the requirements met in order to use the probability binomial probability formula? And remember, given that the subjects surveyed were selected without replacement, the events are not independent. The events are supposed to be independent. Let's keep going. Determine whether the given procedure results in a binomial distribution. If it is not binomial, identify the requirement that are not satisfied. So randomly selecting 50 students and recording how much they like rap music on a scale from 1 to 10. Okay. Remember, the outcomes should be either yes or no. So I guess it probably would be if they said between yes or no. 3 cards are selected from a standard 52 card without replacement. The number of 7s selected is recorded. Doesn't resemble binomial probability function. This is a good question here. So multiple choice questions each have 5 possible answers, one of which is correct. Assume that you guess the answer to 3 such questions. Use the multiplication rule to find the probability of getting it correct, correct, and then wrong. So what's the chances of getting correct, correct, and then wrong? Well, the chances of getting it correct is 1/5. And then the second choice is independent. So there's like 3 trials, and you're going to add them all up. So the chances of getting it correct is 1/5 times another 1/5, and then the chances of getting it wrong, well, is 4 out of 5. I mean, again, if the chances of getting it correct is what a probability of success is 1/5, the probability of getting it wrong is therefore 4/5. And what you could do after that is just multiply those probabilities up, and let's see if it works. Let's clear the entire screen. We'll do 1/5 times 1/5 times 4/5. Unfortunately, this doesn't have the math print on, so I have to use division. It's just the slash mark, and it kind of looks like I'm going to run into the order of operations problem, but the truth is I'm not worried about the order of operations because it does it for me automatically. Division it's evaluating from left to right every time. So that's what I got, 0.032. So the chances of getting 2 correct and 1 wrong is 0.032 if that is the correct answer. Let's check and see. Okay, it worked. Now, beginning with CCW, make a complete list of all the different possible arrangements of 2 correct answers and 1 wrong answer. Then find the probability for each entry in the list. Well, the probability of each entry in the list should be the same as B above. Now, if I were to add them all up, it'd be 0.096, I believe. A less than 10% chance of guessing on all three, randomly selecting and getting two of them correct is already a less than 10% chance. And that probability gets smaller the more questions you do. Okay, so let's look at one more problem and then we'll probably wrap it up. It's pretty much all the same from here. So assume that a procedure yields a binomial distribution with n5 trials and a probability of success of 50%. Use a binomial probability table to find the probability that the number of successes, x, is exactly 3. And so if we don't have any technology at our disposal or batteries fell out, you could use the table and still get it right. So the way the table works is first you need to find the n value. So in our problem, it said that the n was 5. There's 5 trials, and we're going for exactly 3. So we go over to where we see 5 trials, and it lists a lot of the different probabilities, and then we go to where it's exactly 3. So when we have 5 trials and exactly 3, it lists out all the probabilities. There's the table values, but what does it say at the top? Well, these are the probability of successes. So if my probability of success is at 50%, I can go all the way down. Remember, this column is 50%, and exactly 3 is 0.312. So I should be able to get the answer right by doing 0.312. All right, we're going to wrap it up here. Thank you for being a part of this video. Hopefully this was helpful to you, and I look forward to producing more videos in the future. Take care.